Hi, in this video, we're going to take a look at model validation for supervised learning. Okay, so the big idea is that I'm going to build some models and I'm going to take a look at and evaluate my models, but I don't want to use the same data that I built my models on. I need to use a holdout set. I'm going to need to use unseen data that was not used to build my model, to train my model with. Okay, so why do we need to do this? Well, all the algorithms that we use in supervised learning, they're like heat-seeking missiles for detecting the patterns that are in the data. And a drawback of this is that they can overfit. They can over-adapt to the features of, or the aspects of the data that they see when they're going through the training process. And it can work out that if I use the data that I built the model on, I can get the incorrect impression that my model is going to perform very, very well, when in fact it's not, because I have overfitting. Overfitting, my personal definition, is when the model has picked up features in the training data that's not in the population that you're trying to model. And my opinion is that all models overfit. It's a question of degree. Okay, so this unseen data idea is that before I build my model, I'm going to chop up my data into my training data, my validation data, and my test data. The validation and the test data are unseen data sets. Those are my holdouts, and I'm going to put those into the model after I build it, and I'm going to use that to give me a better idea of how the model will actually perform when I put it into production, when I put it into actual use. All right, now to measure overfitting, I don't really have a good metric for you, but here's my personal rule of thumb. I'm going to take a look at my training statistic, take the training data, get a metric. I'm going to take the validation data, get a metric, same metric, get the test data, get the same metric, and I'm going to look at the difference between those. If I see that training is much, much better than validation, or if I see that training is much, much better than test, then I'm going to conclude that I have severe overfitting. Now, my opinion, all models overfit, some more severely than others, means that most of the time the training metric, the training statistic is going to be, frankly, better. So if we're talking about accuracy, we'll have greater accuracy on the training data than we'll on the test data. If we're talking about AUC, we'll have a larger AUC on the training data most of the time than on the test set. If we're talking about mean squared error, we'll have a less mean squared error on the training data than on the test data. Expect this to happen. Now, if it works out that training is, the statistic is not as good as test, then maybe you have an outlier going on. Maybe you have a distribution change. Maybe you should go through and rerun what's going on to get this right. When this has happened to me professionally, it's been typically in an imbalanced data situation, and where, just because of the lack of data, it was just very, very sensitive. And in that project, I couldn't really balance the data because of how my stakeholders wanted things to go. Also, I've had this happen when I've had outliers in my data that I did not properly deal with, or when I had junk observations I needed just to get rid of. So the junk observation being in the training data made the training statistic much worse than I would have expected. So getting rid of the junk observation, fix that. Okay, so what we're going to do, I'm going to take my data set that I have, and I'm going to split it up into 3 groups. I'm going to split it up into training, validation, and test. The training data is used to train the model. Now, the validation data, different people use this in different ways. It's typically used for parameter tuning, if that's the case in what we're doing. So that's typically in neural networks. In scikit-learn, really, we're not going deep enough to even really consider the validation data for this purpose. I mean, there is a validation aspect to the multi-layer perceptron and scikit-learn, but really we're in most spreadsheet problem supervised learning, we're using the validation to as a holdout set to select the best model. We also might use it for like feature selection. If I go through and start doing backwards elimination on on the model, I want to know which version along the path of eliminating unnecessary predictor variables, which version gave me the best performing model. And I would use my validation data to make a decision on which features, which predictors to include, which ones to exclude. Then at the very end, my test set, this is to give me an honest estimate of how the model will perform in production. All right, so here we want to make sure that validation and test are completely disjoint from each other and disjoint from training, especially disjoint from training. Okay, so let's go ahead and get our data. So once again, I'm going to use a heart disease data set that's pre-processed. It's the Cleveland data set. And I'm pulling this from UC Irvine's machine learning data repository. And I'm using pandas, of course. Notice that NA values are just a question mark. And here are the first few rows of the data just so I can see everything is coded as a number. All right, well, here are the categorical variables. Here are the numeric variables, predictor variables to be exact. And we're trying to model heart disease. And here's just a quick describe just so I can see, well, hey, all of these are in fact, coded as numbers. So all of these are categorical data coded as numbers. When I run describe, you'll notice that values that don't make sense I'm getting like an average off of. So I need to do something about this. All right, so let's go ahead and do our data prep. I'm going to make sure that my data is set up in zeros and ones. So here I'm converting over to Boolean, and then I'm adding 0 to convert to zeros and ones. Going to fill in missing values. There's 2 columns with missing values. I'm using the mode off of these because these are both categorical. Now, for the categorical that are binary, I'm just leaving those alone because it's not going to change anything in model performance. But the ones that are not binary, that have multiple levels, I'm going to go ahead and do one-hot encoding, represent these with dummy variables. And we can see the dummy variables set up here. And we can see the distinct values of those categories. All right, and so that's going to give me my predictor variable columns. And here I'm going to get my target variable. All right, so the training data is what I'm going to actually use to build the data. The validation, the test set are held off to the side, not part of the training process, not part of the model building, they're part of the model evaluation. All right, now the validation data, we're going to use this to tune hyperparameters, and I'm going to use this to check to see which model looks like it's going to be the best. Why do I need 2 holdout sets? Okay. In most real life problems, I'm probably going to make hundreds of models through this project. I'm going to do this over and over and over. I'm going to change parameters. I'm going to be doing my parameter tuning. I'm going to be removing and adding predictor variables throughout. I'm going to do this over and over and over. All right, so I'm going to have hundreds of variations of models that I've built. If I only have one holdout set, then more than likely, the one that looks the best on there is because of fluctuations, just kind of like randomness in my data, randomness by how I picked it or how I collect it, how it's just going to work out by happenstance that the best model is by validation or test by just one holdout set, by happenstance, it's then just look better than it really should. So I'm going to get an optimistic result. If I'm going to be building a lot of models in my project, I want to have multiple holdout sets to evaluate. I don't want to use just one. Now, if I'm only going to build a few models, honestly, I can get away with the validation set. Or I can just skip it. I can just have the test set. That's fine. That'll work out as long as I don't need a validation set for something like evaluating the feature selection, or parameter tuning, or just I don't I'm going to skip an additional check. All right, which is especially a good idea if I have very little data. All right, now the test data, this is going to give me hopefully an unbiased evaluation of the final model fit. This is going to be my honest estimate of how the model will perform in production. Now, it is going to work out that we're going to have some optimism in our metrics. First and foremost, we're going to have optimism on our training data. Just take that as ground truth that your training data metrics are going to be optimistic. For example, if I'm doing regression, I'm using mean squared error. I would expect to see my training root mean squared error to be smaller than I would actually see in production. And so the training statistic is optimistic. Now, that doesn't mean don't look at it. That doesn't mean don't take it. That doesn't mean it doesn't have utility. We just need to remember this when we do our interpretation. I do the computation, I take a look. All right, my training statistic is the best that I can expect to see in production. Also, I can take my training statistic, my test statistic, and if they're far apart, if there's a large gap between them, then that's an indication I have overfit my model. I can pump the brakes, I can stop, and I can go and save myself from doing something stupid. Now, the validation data, we can still have optimism on this one, even though this is unseen data. What can happen here, if I've made hundreds of models, which realistically I'm going to do in the parameter tuning process, especially if I'm trying to consider different feature selection aspects. I'm trying to consider different hyperparameters for different models, and I'm trying different model structures. I'm going to create a lot of models in this, and my validation data is going to look just optimistic. And so typically what I do is I'm going to take a collection of some that have better looking values, and then get it down to a short list. Then I'm going to look at the test statistic to see which of these went through 2 rounds of performing very well. Now, the test data, this is where we're looking to get our honest estimate of how it will actually perform in production, but you can still have problems. First and foremost, we can have changes in the relationship between the predictor variables and the targets just over time. This is going to happen with all models if enough time passes. Think about like before and after, or before, during, and after COVID, we had very weird things going on. And so any model I had before COVID is probably not going to be valid, or I at least need to double check it. So if I wanted to go out and take pre-COVID data, build a model and use it today, I probably am exposing myself to some risk. I might have to do that because that's the only data available. But so when I look at the test data, this is not perfect, especially if I have variable leakage. Variable leakage is where I use a predictor variable that comes into creation after the event of scoring, or it would not be available. It maybe exists, but it's not available at the time of scoring. Also, we can have a change in the data distribution. So it could just work out that down the road, where your model is going to perform better, perform worse in certain situations. Imagine I've got logistic regression, and over time, the sample population, the population that I'm going to be scoring off of, tends to move towards like that just 1/2 group, where it's like more like 50-50 instead of solid 0, solid 1 on the model probabilities. Then I would expect to see, just from the change in the distributions, that my model is not going to perform as well. So we always have to keep this in mind. So training will probably give you an optimistic result. Validation can be optimistic also, especially if I have a lot of models I'm building. And test metrics give a more realistic view of how the model is going to perform. But in the future, as things happen, things can change, and it might be that when I actually start launching the model, it might perform worse than when I did my test statistic. And honestly, it's just kind of the name of the game. We're trying to make predictions. We don't truly know if these are good predictions. We can just follow good principles, and on a certain point, we're crossing our fingers and just being hopeful that I get good predictions. All right, so let's talk about alternative ways to do our train validation splits. All right, so the way I like to do things is to have 3 subsets, but not everybody does it this way. Let's say I have very, very, very little data. Let's say that I'm like doing something like the Manhattan Project, where experiments are super expensive, super hard to get data, and I need to milk every bit of information out of that data. Well, if I've only got 10 observations, I can't do a train validation split. I just don't have the data. In fact, train only is actually the classic way of handling supervised learning by statisticians before computer scientists even got into this game. Back when we're doing like hidden figures, pencil and paper, the statisticians were going to be doing train only. There was no validation, no test splits. After data became more available and we had more observations, more rows, larger data frames, then we had the luxury of doing a train validation split. Now we can also do just a train test split, and this is what's most common in the Python community, that they're not doing the validation. I personally do validation, but whatever you do, you know your situation best, go for it. Train test, this is very reasonable if I'm only building a few models. I'm not going to go through this full extensive process, or my stakeholders say, I want logistic regression with these predictor variables. There's no point in me going through this extra step. I'd rather have that extra data to get a better model estimate. Oh, something I have to say, if I'm using data in validation or test, I'm not using it in my training data. It means it's not being involved in the model fine-tuning process. And because of that, we can have a weaker performing model. Honestly, we want ideal situation. I would have an infinite amount of data to put into training, validation, and test to make to get the best model I possibly could. Realistically, we don't have that. If I'm taking a data point from train and putting it in validation, or I'm taking a data point from train and putting it in test, then that is one less data point to give me a better actually fitted model. You have to balance what's going on. You have to balance the tuning of the model, the fit, with an accurate idea of how things are going to perform down the road. And in the Python community, typically they just do a train test split. All right, so now another idea, and this one, people have discussed this and there's disagreements. My boss is on one side of the fence, I am on the other on this. So after I go through, I take my training data and I do my validation and my test statistics. Some data science, including myself, like to go back after I got my estimates and combine all my data, refit the model, and this is the actual model I put in production. Why do we want to do this? Because we want as much data to get the best fitted model possible. Now, my boss, who is a very good data scientist, and I totally have faith in him, he doesn't like that because the test statistic is not on the model you're putting in production. So he wants to know exactly what's going on before he puts the model in production. And so he would rather have less data for training, but have a better, more confident idea of what this exact model is going to do when it's launched into production. We can also do a refitting with our validation and our train data. Whatever you choose to do, you know, it's a subjective decision on what's best. So if I'm going to use the original just training data, I'm not going to refit after I've gone through. I could also refit on training and validation, or I could take all of my data and refit on the whole thing. When I do this, I'm going to have no validation statistic. I'm going to have no test statistic on the actual model that goes into production, just the ones that I built to help me decide what's the actual final model. Now, by default, in the carrot package of R, it actually refits on the entire data set. And if I want to, go a little bit deeper, I can use index final parameter in the train control function within train to prevent refitting if I want to. Another option that we have, this is observations in more than one set. This is usually a bad idea, but imagine that I'm in the situation where I have tons of data, I have a balanced asset, everything is rainbows and unicorns and sunshines and butterflies. So then I don't care about, the partitioning of my data. When I partition my data, each observation is in one of those sets, and each observation only appears once. It appears in exactly one of the three subsets. Well, if I'm in a very small data set, or I have a very, very severe data imbalance, I might choose to repeat the low frequency levels inside multiple partition sets. So it technically would not be a partition. This is generally to be avoided. It's better to not do it this way, but this is an option that we have in case we can't use other techniques. So for example, a lot of people like to use SMOTE, use synthetic data to get around situations like that. Well, maybe I'm in a legal situation where I can't use SMOTE. SMOTE is fake data. It's synthetic data. I personally believe you should avoid using it. But maybe I can't use it. I wish I could. Then it might be better to break this partition philosophy and repeat the low frequency levels across multiple subsets. It's a tool in our tool belt. I would avoid using it if I can, but there's a time and place for it. All right, so let's go through the scikit-learn methods for selecting training and validation data. So I'm going to change this. I'm going to do an edit on screen. All right, so I'm going to be building a logistic regression models for you to show you some stuff, and I'm going to use AUC to evaluate model performance for this. All right, so first one is going to be that manual partitioning. This is how I prefer to do it. This is not a built-in function in scikit-learn. I like to actually randomly assign train validation and test if I can. Sometimes test will be like a holdout set of most recent observations, and I'm going to randomly assign, and then I'm going to go for it. Now, how I like to do it, I like to have a column in my data frame saying which subset each observation is. That is my preference to do this because it keeps it all nice and neat and clean. I don't like to have a lot of objects floating around in my workspace. I find it's better to have everything that can be done within a data frame should be done within a data frame, but not everything can. All right, so when I do this, I'm basically going to just print a bunch of stuff to show you what this is like, to give you an idea of what this looks like. If I do the partition, the first 10 are random validation tests and train values. So here's the first 10 from this part of the code. Here I'm storing the partition on the data frame. And now just to show you what it looks like, or how I pull this, you notice I use LOC. Remember, LOC is for logical, LOC is for index. And so here I'm just saying when it's train or validation or test, I'm going to get my corresponding predictor variable values. And so we have, here is for train, validation, and test. All right, so let's go ahead and fit a logistic regression model using the training data. Notice that I'm using the training data for this. And then I'm going to compute my train, validation, and test statistics. Okay, so we have 92 for train, 94, that's rounding, for validation, and 88 for test. So you'll notice that there's a bit of a gap between train and test. This is honestly, that's still like typical, but I would prefer to see a little bit closer. The default setting for logistic regression is to do ridge, and so it's minimizing the coefficients in terms of an L2 norm penalty. Purely from a math point of view, we will never get a 0 for a coefficient off of ridge. Now, another technique is bootstrap. This is how the default setting is in R's caret package. Okay, what we're going to do here is that I'm going to do sampling with replacement on the index of my data frame. So I sample with replacement the same number of observations as I have in my data frame. So if I have 1,000 observations, I'm going to sample with replacement those observations 1,000 times. Some of them are going to appear multiple times. All right, well, if I'm sampling I've got 1,000 observations and I sample 1,000 of them with replacement, some get in there multiple times, some of them have to get left out. All right, so the ones that get left out in the bootstrap ends up being our holdout set for this. So this will be our test set. Here from this point of view, I'm talking about train and test only. For validation, usually we have to do a little bit more manual work on this, especially if I'm using scikit-learn. Scikit-learn just takes the point of view of train test, that's it. Okay, so another nice thing about Bootstrap is that I can do this over and over and over, and I can get a distribution of my metrics to make me more confident what's going on. This is a really good idea if I want to make sure that when things look good, it's not just kind of a fluke, with the data, that things are actually going to perform as I intend. All right. And so I can do this repeatedly over and over and over, get distribution of, like for here, my AUC for train, get a distribution for my AUC for validation, or sorry, for the holdout set, and it'll look pretty good. All right, so just to show you what the training set looks like again, here's my training set. Here are the predictors. Here is the target variable. Now, these were sampled with replacement. Some of these are in there multiple times, and you'll notice that they've been like shuffled because of how I did the sampling. I didn't go through and reorder them. Now, here is my holdout set. Now, the holdout set, I'm looking at everything, all of the indices that were not selected in that bootstrap selection process. And so I just say, hey, if it's not in the selected observations, go ahead and put it in the holdout set. That's exactly what I did on this step. All right, so when I do that, the training data is going to get shuffled by how I did this. I could have sorted and they wouldn't have been shuffled, but I would have repeats. And here are all the observations in their original order that did not get selected by the sampling with replacement, the bootstrap. All right, so let's go ahead and get our training AUC, so 95, and our test AUC of 90. Now, just to emphasize that I don't always have to do the split. I'm putting this one here as a technique to evaluate model performance. Here I'm talking about this part of the video, the partition, bootstrap, none, and out of the bag. I'm talking about more of the manual ways to do things, manually splitting. I'm about to start talking about the tools that scikit-learn provides. So remember, I always have the option of not having a holdout set. This is typically done when I have very small data. This is a bad idea if I have the luxury of doing a split, but it's always a tool in our tool belt. Now, out of the bag, this can only be done with a boosting algorithm, such as random forest. Random forest is by far the most common use of this. Okay, so when we are doing, so not boosting, bagging, I meant to say bagging. When we do bagging, what we're going to do, we're going to take a subset of our training observations on each individual tree. Most of the time, most implementations of random forest are going to actually do a bootstrap on our observations. Well, what's going on here? I'm going to do a forest of decision trees. Each individual tree gets its own bootstrap, or it gets its own subset selection, depending on which parameter I put in. So most of the time with random forest, I'm going to be doing a sampling of my observations, either bootstrap or just straight subsample for each individual tree. So therefore, each individual tree is going to have a holdout set. Well, I can go and I can evaluate the holdout set on that individual tree. So if I have 500 trees in my random forest, I have 500 different holdout sets. I have 500 different bootstrap training sets. All right, so we can go in and use these predictions as a surrogate, or as a replacement for a validation and test if I need to. Now, to get access to these, we want out of bag decision function to be held on to. Now, when we do this, we have to have OOB score set to true, and we need to have random forest. Sorry, in random forest, we need to have boosting set to true also. And so by default, bootstrap is already on true, so I just left it as is. But out of bag score by default is set to false. And so I can get the value. So for train, I have 0.92, and for test, I have 0.89. Now, there are plenty of functions in scikit-learn that will do the splitting for us. All right, so we have a train test split. So what this is going to do, this is going to walk up and it's going to randomly split the data, and it's going to preserve the order that I originally had it in my data frame. Shuffle split is going to do a random permutation cross-validated. Stratified shuffle split. All right, so this is shuffle split where we stratify by the target variable. And so here, the stratification needs to go by the target variable value. All right, k-fold is what I'm going to do is I'm going to say, all right, I'm going to partition my data into subsets. Typically, we use 5 or 10 are the most common. I'm going to walk up and I'm going to randomly partition my data into 5 different subsets. What we're going to do, first one is the test set. The other 4 are train. Second go around. Subset 2 is test. The other 4 are train. Third go around, the third subset is test. The other 4 are train. Fourth go around, the fourth subset is test. The other 4 are train. And then last but not least, the fifth subset is test. The other 4 are train. And that is k-fold cross-validation. And here we're going through and we're just randomly assigning each observation, each of these. Now, stratified k-fold is k-fold where we make sure that we have even representation of the different levels of the target variable. Now, if I have imbalanced data, this can be very hard for it to actually accomplish. It may not actually work out, but it will do its best. Now, repeated k-fold, remember that we randomly assign to each of the subsets. Well, I can just repeat that over and over and over. And by doing that, I can get a distribution of my train and test statistics and get a better idea of what's going on. If I'm using k-fold, I automatically, assuming k is a meaningful value, like typically 5, the larger the K is, the more of a distribution I have for what's going on. Now, a disadvantage to a large K is that if I have a large K, I have more overlap in my training data. Think about twofold cross-validation. Twofold, I do two different models. On the first step, half of it is train, half of it is test. The other step, this becomes train, the other one becomes test. And so there's zero overlap, and that it helps, helps me identify like the full variability of what potentially can happen. If I keep on having overlap, like let's say I have a very large K for the folds, then really my training data kind of all looks the same across all of the submodels. Now, for group K-fold, here we're going to have like some subgroup, maybe like a blocking variable that we want to make sure gets accounted for in our partitioning. Once again, we can do stratified group K-fold. Now here we can do leave one out. Leave one out cross-validation is cross-validation with the number of folds equal to the number of observations. For each observation, I'm going to pull it out. Everything else is the training data. I'm going to check how that model performed on that pulled out data. All right, so if I had 100 observations, I would be building 100 models in this. Each time I'm removing one observation, everything else is in the training data. That one observation is my test data. This is computationally expensive. This can take a long time. So when I use leave one out cross-validation, typically we have very, very little data and when we do this, or there's a special exception to this. It works out that multiple linear regression has a special formula using the hat matrix to compute this very fast. Okay, and so using some matrix algebra for multiple linear algebra or multiple linear regression, I have a special formula. In general, if I'm not doing multiple linear regression, I'm not going to use leave one out unless I have very, very small data, which might be it. Now, leave P out is where we cover all possible subsets of pulling out two observations if P is equal to 2. P is equal to 2, I'm going to go through and combinatorially find all possibilities for pulling two observations out. If P is equal to 3, I'm going to find all possibilities for pulling out 3 observations. This can take a really, really, really long time. The closer P is to n divided by 2, and is the number of observations you have, the longer this is going to take. Now we can also do leave one group out. So here, if I have like that blocking variable, I can pull out one level of the blocking variable, use that as a holdout set, use everything else as a training set, and that's leave one group out. Now leave P group out is just I leave multiple groups out and go through the same process using all possible 2 combinations or 3 combinations. Now we have group shuffle split. Once again, this is shuffle split using groups. Now also the groups are a variable that is not predictor variable and is not in the model fit like a control variable and is not a target variable. So when we have this external group, if I'm going to be partitioning into subgroups like this, this subgroup for this purpose of splitting needs to not be one of the variables used in fitting the model. We also do a time series split. All right, so in the time series split, what we're going to do is I'm going to chop up into, let's say we do fifths. I've got 1/5, 1/5, 1/5, 1/5, 1/5. All right, I'm going to build my model where train is 1/5, 4/5 is test. Then I'm going to build my model using 2/5, 3/5 is holdout. Then I'm going to build my model using 3/5 as train, 2/5 the last 2/5 as test, and then I'm going to finally build my model using the first 4/5 of the data as train and the last fifth as the holdout set. And so with this, what I'm doing is I'm basically deciding, hey, I'm going to cut somewhere. Everything before the cut is training, everything after the cut is test. Now we can also have predefined splits. And so this function, let's say that I went and did the random assignment like I did at the beginning of the video. Then I could go through and use the predefined splits manually like this. I never use this. I just do it, you know, the regular way. All right, so to do a train test splits, you know, I just go and use, this is by far the one that is the most common in the Python community. And so here we can see we have a 93 and a 91 on test. Shuffle split just invokes, you know, some shuffling in on it. I'm just going to start scrolling through this because I've built up the code so that you can go back and see how I did it so that you could execute. I always give you functioning code. Another thing I need to say is that when I'm chopping up my data into subgroups, if I have imbalanced data, whether that's with a predictor or a target variable, it's possible that things can get missed. So let's say that I had imbalance, you know, predictor variable where I had 99.9% females and a fraction of a percent of males. When I go and I do my splits, it's possible that I don't get any males inside a split, and so that can cause some problems with like the dummy variable aspect. So, and the fitting, because it doesn't even have an opportunity to detect it. And here's k-fold. Stratified k-fold works to evenly distribute the target variable levels. Repeated k-fold, this is the one I like the most, where I would just do it over and over and over. We have to specify the number of splits and the number of repeats. So here I'm going to get 10 training statistics, 10 test statistics. And so I'll have like a distribution that I can look at to get a better idea of how my model is going to perform. You know, repeated, stratified k-fold, and so on. Group k-fold. You know, I talked about all these already. Leave one out. Remember, with leave one out, don't use it unless it's either small data or it's multiple linear regression, and I'm going to use that special formula. It takes a long time. All right. Oh, okay. Now the one I want to show you the most at this point is a time series split. So you'll notice that here the index is from 0 to 52. On the next split, so this is my training data. My next training data is from 0 to 52, but then keeps on going to 102. So it picked up 50 more observations. On the next split, you'll notice that I get, you know, 0 through 102 again, but once again, I pick up 50 more observations. Each time we have a split, it keeps on increasing. And you notice it put, you know, when the division didn't quite match up with the numbers, it put the remainder in that very first set to give me a larger training set. And then I get, you know, 4/5 of my data, a little bit more, just a touch more, and then I get my full data set. And that's how the index of the training data is going to be. The test will be everything that's to the right off of this, the later observations. All right, so now how can we pick our test data? So here I've shown you random selection. So here we're saying that I want the distribution as much as possible for train validation tests to be the same. This is by far the most common one. We can also do a time-based selection. Currently I'm working on a project and we're using the last year as our holdout set because that year is going to be our best representation of what will happen in the future. All right, so what this does for us is that this gives us as much confidence in the metric of how the model will perform. A disadvantage to this is that my last year of data, I assume, is my best representation of the future. Well, if that's my best representation of the future, I would like to actually be using that in my training data. By putting it in test, I'm not using it in training. This means that I have more confidence in the statistic itself, but honestly, I don't care about the actual statistic. I care about the model. If I had the world's greatest model and I didn't know it was the world's greatest model, but I put it into production, I would be super, super happy. I'm happy to be ignorant if I'm going to get a good result. So make your choice, whatever is most important. We can also go off of an important subset of our data that we absolutely have to nail it. All right, so for your homework, for those of you who are taking the class at University of Central Florida with me, try at least 3 of these techniques to partition your data, compute your train validation test statistics as appropriate. If you just do train tests, just do train tests. Specifically, I want you to look at the gap between train and test. Double check to see if you have overfitting. If you have overfitting at this point, I mean, it's not a problem. You don't have to go through and do the model tuning. I want you to spot it. I want you to see it. I want you to, try and make a call like, hey, that's close enough or that's not close enough. All right. Well, that's all I've got for you. Life is short. Do math.